Now we'll continue where we were in the reduction of our array. We saw the max, the min, np.max, np.min, np.sum, and we'll see that np.argmax, which returns the index of the maximum, and np.argmin, which returns the index of the minimum, and we'll specify the axis along which we want. So we'll see that the maximum values index along axis 0 is this 0, 0, 1. Similarly, in the minimum, this is corresponding to this 0, 0, 1, and the minimum is along axis 1. So this is the minimum, and this will be these two elements will be printed, and that's why 0, 1. We can find the standard deviation by np.std, and we can use the np.line alg package to find the norm. So this is the norm of the array. Now we'll show that how we can compare element wise comparison by using these signs. We can just simply put the arrays, and we can use these signs: greater than, less than, not equal to, and store it in the third array. These are two arrays. First we'll see that whether array 1 was greater than 2. We'll compare element wise. So if these two elements 0.95 is greater than 0.57, it's true. 0.45 is less than 0.82, so it's false and corresponding element wise. Similarly, we'll see the less than and in the same way we'll see the not equals function. Now we'll move on to the another. We'll find that .all, .any is comparing that if any element of array 1 is greater than any element of array 2. So will come there obviously exists any element in 1 which is greater than any element in the array 2, so it returns 2. Also we can do the second: does all elements of array 1 are greater than? No, they are not. Some of them are less than, so that's why it returns false. Also we can do similarly the use of not equals to, and by using .any and .all. .any checks any element and .all checks all element. It returns boolean values. Now we'll go into vector or the matrix multiplication. First we'll see that how two vectors are multiplied. They can 1D arrays or vectors can be multiplied by using np.matmul or by using this @ symbol, and this is array 1, array 2, and mat multiplication of the two arrays is this. It's a scalar, and mat multiplication of two arrays by using @ sign is the same, and the dimension is 0 or the 1. Now we can see that matrix and vector multiplication, they can be done by the similar np.matmul and two matrices can also be multiplied by using the np.matmul. Now the matrix multiplication with dimension, we have seen that when two matrices are multiplied they have a shape. So this is the matrix 1 with the with this dimension, matrix 2 with this dimension. So 3 and 3 will be cancelled and the final will be 2. They are derived by using np.matmul. Now we'll move on to the dot product of two elements. Now dot product cannot be carried for 1D vectors because they have dimensional issues. Now we'll see that for 2D it's same. np dot, by using np dot we can multiply two matrices, or by using this sign, this is matrix 1 of this shape, matrix 2 of this shape, and dot product two matrices divided by np dot. This is the operation, and by using np dot similar can be found at by using @ the same result. Now we'll use two arrays of dimension, multiple dimension. These, the dot product can be carried out by using that np.matmul, not np.dot. Kindly note. By using this and storing this and the shape of both of the arrays, kindly note that in multidimensional only the last two will be considered as a multiple matrix multiplication, and we can see that 4 and 4 will be cancelled and the final will be 9 5 7 3. Now we will finally go to the tensor dot, which when we input arrays and the respective axes along the sum reductions are indented, the axes that take part in sum reduction are removed. We'll see this by an example. We see that these are two arrays of these shape, array A and array B. We can compute the compute tensor dot product along specified axis. So np.tensor dot AB, the axes are these along which we need elimination. So we'll see this, A's dimension is this, B's dimension is this, and the final dimension is 5 and 2 because the rest of the dimension are removed because we have specified these. We specified that we want elimination of these axes, the 0th, the 1, and in the second we want these and these to be removed. So we specified it, and then we got the matrix multiplication or the dot product basically. With this we end our lecture. Thank you so much for joining. I hope you have understood everything. Kindly go through the notebook and you'll go through and understand better when you practice these things on your own. Thank you.